today on Impossible Engineering, the Airbus A380, the largest passenger plane on the planet.
When you see that huge monster, impossible that this big thing is gonna fly. No way.
It took cutting-edge aerospace engineering.
A massive fly-by-wire system like this is an incredible tool of safety for the aircraft itself.
And a revolutionary design.
Without those design features, this aircraft wouldn't exist today.
To make the impossible possible. Since the birth of aviation over a century ago, air travel has been growing exponentially across the globe. Over 3 billion people fly each year. That's half the world's population. The challenge for today's aerospace engineers is to find a way to keep up with the constantly growing demand and design aircraft that can accommodate as many passengers as possible.
15, 20, 30 years ago, the challenge in the aeronautical field was mainly speed. Then the new objective of Airbus, Boeing, for example, was the size of the aircraft.
In order to reduce the 100,000 flights that take place each day, aircraft designers would need to think big. What they came up with? Smashed aviation records. The Airbus A380, an ultra-high-capacity airliner, the largest passenger plane on the planet. An aircraft so big that a giant building had to be constructed just to accommodate it.
We built that brand new hangar to welcome that huge monster, that huge aircraft, so big that our hangars couldn't fit that kind of aircraft.
This revolutionary double-decker plane has an almost 265-foot wingspan, the largest of any commercial aircraft. It has almost 6,000 square feet of usable floor space. That's 40% more than the next largest airliner. It can carry up to 850 passengers. And with its state-of-the-art jet engines and cutting-edge design, it can fly non-stop, almost halfway around the world. At a custom-built hangar in Paris, this Airbus A380 is being stripped down as part of its scheduled 4-year service, revealing the secrets behind this incredible feat of engineering. For maintenance manager Sylvain Fargo, this incredible machine never fails to impress.
The first time when I see it, the first word was wow, and it's still wow when I see it. This aircraft was part of what we could call a jump in the aeronautic industry. New technologies required from us to train our mechanics, our engineers, so it's quite a step through the future.
The A380 is a colossal machine that's the result of centuries of innovation. Man has been trying to fly like a bird for quite some time. But flight isn't as easy as it looks. 11th century Benedictine monk Elmar reportedly strapped wings to his back and launched himself off Malmesbury Abbey. but he glided out of control, coming to a painful landing. And in 18th century Paris, the Montgolfier brothers discovered that hot air could make a paper bag rise. This led them to build a hot air balloon, making history with the first ever lighter-than-air manned flight.
Oh, très bien, magnifique.
But their design had a few drawbacks. To build a flying machine heavier than air that can take off and remain airborne, engineers would need to figure out a way to harness the forces of nature. And in 1804, British scientist Sir George Cayley finally unlocked the mystery of flight, earning him the title, the Father of Aeronautics. Cayley discovered that while in flight, a bird's wing has a curved shape. This is now known as an aerofoil. Air passing over the curved surface speeds up, losing pressure. The pressure of the undisturbed air below remains high. This creates upward force. By turning the aerofoil upside down, aerospace engineer Dr. Ben Evans can demonstrate how Cayley's shape successfully conquered the forces of gravity.
Now, in this experiment, on one side, we've got weights representing gravity, the force that needs to be overcome. And on the other end, an aerofoil. And as this spins, the arm goes level. The air passes over the aerofoil and pulls it down to counteract gravity, which is what lift is trying to do in an aircraft.
In 1853, at the age of 79, Cayley put these ideas into practice when he launched the world's first heavier-than-air manned glider. Sir George Cayley had made the impossible possible.
It's amazing what you get it to do when you know how.
Cayley's achievements inspired generations of aerospace engineers to reach for the skies.
By doing some very simple experiments, he managed to show what allows a wing to generate lift, just like the wing of this glider that is allowing us to hang here in the skies.
Without George Cayley's innovative wing design, the gargantuan Airbus A380 wouldn't make it off the ground.
When you see this aircraft, it's so huge, you can say, but impossible that this big thing is gonna fly. No way. But in fact, it's only aerodynamics.
The A380's wings apply the same principles that Cayley exploited, but on an enormous scale. With an almost 265-foot span and a surface area of 9,095 square feet, they're big enough to park 20 of Cayley's gliders on top. But engineers needed some serious power in order to get the world's largest passenger plane airborne. So they looked to a revolutionary design from the past.
What an incredible sensation! And a feel the acceleration pushing me back into my seat.
To produce more impossible engineering. In a supersized hangar in Paris, an Airbus A380 is being serviced. Technician Charlie Jackson is getting up close and personal with this engineering masterpiece.
As this aircraft is taking off down the runway and generating speed, the tips of the wings actually will raise up, which is a sign that the wing is generating the lift that it's going to need to carry such a large aircraft into flight.
Creating a wing big enough to generate lift, but small enough to minimize drag, is an engineering conundrum. On the A380, special high-lift devices, slats on the front and flaps on the back, allow the wings to increase in size and curve depending on how much lift is needed. But the wings also keep the A380 airborne in a more surprising way.
Inside of these wings is the fuel, which you need to complete your flight.
The plane has 11 fuel tanks, 5 in each wing and 1 in the tail. Fuel is stored in the inner tanks to reduce weight at the wingtips, but after takeoff, it's pumped to tanks across the whole wing. Throughout the flight, the system constantly adjusts the fuel to maintain the center of gravity.
This wing is the product of good design. If it hadn't been that way, it just wouldn't be practical to make an aircraft that size.
Well-designed wings aren't enough to keep this massive plane in the air. Creating engines powerful enough to lift a 369-ton aircraft, along with 200 tons of passengers, fuel, and cargo, almost 2.5 miles into the sky, is a daunting task.
The engines are one of the most important components on this plane. It's like the heart. It doesn't beat, the body doesn't live.
Powering the A380 would be impossible without the brilliant work of past engineers. By the late 1800s, aerospace engineers recognized that power and thrust were needed to fly. In 1874, Frenchman Félix de Temple attached a steam engine to a monoplane.
Et voilà!
But the engine was too heavy.
Sacré bleu!
And in 1903, American professor Samuel Langley tried using a giant catapult. But the takeoff didn't quite go as planned.
Ah, shoot!
Luckily, 2 siblings from Dayton, Ohio, were about to make one of aviation's most significant breakthroughs. In December 1903, Wilbur and Orville Wright launched the maiden flight of the Wright Flyer. Two propellers driven by a piston engine gave the plane enough thrust to take to the air. Even though the flight only lasted 12 seconds, covering just over 100 feet, it was the first controlled powered flight and is recognized as the birth of modern aviation. But getting a plane more than 1,500 times heavier than the Wright Flyer airborne would take an incredible engineering breakthrough. Through the late 1930s, piston engine propeller planes were the aviation standard. They were limited in range, speed, and altitude. However, a radical engineering innovation was on the horizon.
What an incredible sensation!
Dr. Ben Evans is experiencing firsthand the power of Britain's first fighter jet, the Gloucester Meteor. It's powered by the first ever jet engine, which was invented by British engineer Frank Whittle.
I can feel the acceleration pushing me back into my seat. And these 2 engines kick into work either side
Whittle's engines were powerful enough to lift the Gloucester Meteor over 7 miles into the sky at a speed of over 600 miles per hour. As groundbreaking as the jet engine was, the engineering behind it is surprisingly simple.
In essence, the way the jet engine works is you have suck, squeeze, bang, blow. You suck air in at the front here, and then that passes through a spinning compressor. And that compressor squeezes the air down, increases the pressure and the temperature of the air before it passes in to the combustion chamber. Now, this is the point where the fuel is added and ignited. This increases the temperature and the pressure of the gas even further. And then all of those hot exhaust gases have to expand, speed up through the back of the engine, and they pass through this turbine. And the turbine is connected via a shaft down the center of the engine to the compressor at the front, making that spin. But what pushes the engine forward, what generates the thrust, is the expansion and the acceleration of the exhaust gases out of the nozzle at the back of the engine.
Whittle's jet engine allowed aircraft to fly faster, higher, and farther than ever before, changing the face of aviation forever.
So successful was Whittle's design that the jet engine has just become a standard now on modern commercial transport aircraft. The dream of travelling faster, higher, safely, and more economical all over the world became a possibility.
To power the Airbus A380, engineers would need to take Whittle's jet engine design and supersize it.
That size of aircraft couldn't exist before, so they had to develop and to design brand new engines to suit what's required to have it going upstairs in the air.
While this A380 is being serviced in a giant custom-built hangar, technician Charlie Jackson is getting the chance to examine the jet engines that power this massive plane.
The A380 has 4 huge engines, 70,000 pounds of thrust each, full of new technologies. It's one of the most advanced engines that's available on the market today.
The A380's 4 specially designed GP7200 turbofan jet engines are among the most powerful ever built. They're nearly 50 times more powerful than Whittle's jet engines, and draw in enough air to inflate a hot air balloon in 3 seconds. But for the engineering team behind this colossal plane, it wasn't just about power.
The main difficulty is to define an engine that is powerful, that gives economy to the airlines, and reduce noise.
Thanks to its state-of-the-art design, the A380 burns 22% less fuel per seat than the average 747 jumbo.
These fan blades have been designed specially for this aircraft. They have a very revolutionary new shape to increase the airflow through the engine. 70% of the thrust from the engine actually comes from these blades, and not from the motor itself, which is burning the fuel and turning these blades.
The 24 hollow titanium blades are boomerang-shaped with a reverse sweep at the tip. This shape slows the air from supersonic to subsonic speeds, making the A380 more fuel-efficient per passenger than a car, and also much quieter.
This aircraft is well below the limits of noise for the size of the aircraft, really setting the standard.
The Airbus A380 is the biggest passenger plane ever built. Capable of flying non-stop for almost 10,000 miles. It's a triumph of aerospace engineering.
Getting an aircraft of this size off the ground to fly practically halfway around the world is an engineering feat.
The aircraft's huge traveling range is mind-boggling. It also presents designers with a unique challenge. The A380 is capable of flying from Dallas to Sydney non-stop. These lengthy flights require extra provisions for passenger comfort. Its two passenger decks provide almost 6,000 square feet of floor space. That's about 3 tennis courts. At a custom-built hangar in Paris, this Airbus A380 is being stripped down as part of its scheduled service, revealing its engineering secrets.
It's quite impressive to fly on this aircraft. As you can see, it's a very long aircraft. In the business class, you have 80 seats. That's quite important.
But designing an airplane for comfort isn't a new idea. One of aviation's earliest and most successful innovators set the bar. Early aviators who took to the skies had little choice but to bundle up and brave the elements. But one man had a different idea. In 1913, Russian engineer Igor Sikorsky built the Ilya Muromets, a plane designed specifically for luxury travel. It was the world's first airliner. He used a wind-driven generator for electricity and ran pipes of hot air from the engine through the cabin for heat. There was also a bedroom, toilet, and comfy seats. 16 passengers could travel up to 370 miles in style. The Ilya was redesigned as a bomber to fight in the First World War. But its luxurious legacy lives on and has led the way to a new world of aviation possibilities. Just like the Ilya Muromets over a century ago, the Airbus A380 has redefined air travel. With its ability to carry hundreds of passengers in supreme comfort for over 10,000 miles.
When you see at the aircraft outside, it's so big that when you come in, when you have a seat, you can imagine how loud it's gonna be when it's gonna take off. But in fact, no, it's quiet, and you don't even know you're in the air.
But for a plane as immense as the A380, traditional building materials won't cut it.
If the whole airplane had been made from the traditional aluminum, it would have been catastrophic to the design.
So engineers had to revolutionize this approach too. The Airbus A380 is one of the most technologically advanced commercial airliners in the world.
The technologies used in the design of this machine were not existing 20 years ago.
But for its design team, redefining the limits of modern aviation meant overcoming some seemingly impossible engineering challenges.
They told everybody in the world that they will build the biggest aircraft in the world, so it was quite a challenge for them.
And one of their biggest challenges relates to the plane's record-breaking size.
forces that an airplane are subjected to on any flight are severe because it's having to expand, it's having to contract, it's having to deal with extreme temperatures. Even the aircraft is actually getting torsional effects on itself while it's flying through turbulent situations.
Since the 1920s, aluminum has been the material of choice for aircraft skins. It's flexible, strong, and light. But when you're building the largest commercial airliner in the world, every ounce counts. Just the paint alone weighs half a ton.
If the whole airplane had been made from the traditional aluminum, it would have been catastrophic to the design. It would be way too heavy. They would have had to have bigger engines, they would have had to have bigger wings, it would have burned a heck of a lot more fuel, and it wouldn't fly very far.
Decreasing the weight by reducing the thickness of the aluminum skin wasn't an option. Engineer Ben Evans demonstrates why in his lab at Swansea University.
So this gun is going to fire these baseballs at high speed at our target in the stand, and we'll find out how much damage they do.
This aluminum sheet is approximately half the thickness of a traditional aircraft skin.
Wow, let's have a look and see what's happened. And there's the damage. It's deformed this by a good 5 centimeters or so. So really quite a lot of damage with that impact on the aluminium sample.
The designers of the A380 needed a material that was as strong as traditional aluminum, but lighter.
They needed to find materials that could create such a large aircraft that wouldn't weigh like a tank.
Solving this engineering conundrum would have been impossible without the trailblazing work of a great engineer from the past. In the 1930s, American engineer Virginius E. Clark created an alternative to aluminum. He infused birch board with phenolic resin and laminated it under extreme heat. He called this new material Duramold. Used in Howard Hughes' enormous Spruce Goose seaplane, Duramold was one of the earliest and most successful examples of an aviation composite.
Composites are made up of more than one material and take advantage of the best of both worlds. What we're going to do to prove this is the case is impact test a composite.
This composite is a woven carbon fiber infused with epoxy resin, the same thickness as the aluminum Ben tested earlier.
Literally nothing. So that impacted right here, bang in the middle. In fact, there is absolutely no sign that any damage has been done. So these are the results. This is the composite, this is the aluminium, the same impact force, but look at the damage on the aluminium. So that is a result for the composite. A lighter material and a stronger material. And that is why this stuff is being used by aerospace engineers today.
To build the world's largest passenger plane, engineers took Virginius Clark's innovations with composites to the next level. They developed a brand new material for the Airbus A380, glare. Reinforced with glass fiber. It's thinner than aluminum.
The composite materials that make up this aircraft, they're as strong as the traditional materials, and they're as flexible as the traditional materials as well. To give an example of how sturdy they are, there's more than 1 ton of air pushed inside this aircraft when it's flying, when it's pressurized.
The use of glare reduced the overall weight of the A380 by 15 tons, allowing this massive plane to be light enough to fly.
If they hadn't used glare or a similar composite, the aircraft that we have today probably wouldn't exist.
The A380 may be able to fly, but its ideal wingspan is too large for the world's airports. So designers had to take a classic engineering solution.
Often in engineering, the simple solutions are the best solutions.
And give it a 21st century twist. The Airbus A380 is a triumph of 21st century aerospace engineering. It's the largest commercial airliner in operation today. At a state-of-the-art custom-built hangar in Paris, this A380 is undergoing its scheduled 4-year service, giving technicians a chance to get intimate with this colossal machine.
It's a big aircraft. You cannot imagine that it's going to go and fly so easily.
It's not just the materials on the A380 that make it stand out from the crowd. Even the method of construction is groundbreaking. Sections of the A380 are built in France, Germany, the UK, and Spain, then transported to Toulouse for assembly. Moving these parts requires custom-built ships and the use of Airbus's A380-800 Beluga supertransporter plane.
When people are waiting to go inside the aircraft, you can see children looking at it. People are really excited.
The ideal, most efficient wingspan for this massive aircraft is 270 feet. But aviation regulations state that all planes must be able to fit into a 262-foot box. If engineers didn't come up with a way to shrink the A380's wings, it would be too large for the world's airports. Their solution was found in a great aircraft innovation from the 1970s. In 1973, the world was in an oil crisis. An embargo on sales to the West saw prices quadruple overnight. The aviation industry was paying the price. A solution was desperately needed to improve airplane fuel efficiency. And aeronautical engineer Richard Whitcomb found one while working on NASA's Aircraft Energy Efficiency Program.
Aerodynamicists are always trying to improve the efficiency of wings, which really means trying to improve the ratio of the lift to the drag of the wing. One of the things that was causing a lot of drag and dropping the lift on the wing was what's called a wingtip vortex.
This wind tunnel is simulating an ordinary wing traveling through the air at a typical cruising speed.
In the central section of the wing, you can see that the smoke is very smooth until it reaches the tip of the wing. And once we're at the tip of the wing, you can see this vortex pattern forming.
A wingtip vortex occurs when high-pressure air under the wing spills upwards at the tip to meet low-pressure air above. This leads to turbulence and drag, forcing the engine to work harder. Richard Whitcomb's idea was to change the design of an aircraft's wingtips into vertical winglets. The winglets create less drag and burn less fuel.
As I move the smoke trace towards the end of the wing this time, instead of having the single strong vortex that we saw in the case without the winglets, what's happening now is that the flow is smearing out almost into a sheet, making the wing more efficient.
Adding a winglet prevents the mixing of the two airflows above and below the wing, reducing the vortex. The A380 has specially designed arrow-shaped winglets called wingtip fences. These allow the wings to be shortened to just under the maximum allowed 262 feet without compromising the aircraft's efficiency.
Without those design features, this aircraft would be way too big, it wouldn't be practical, and it wouldn't exist today.
The Airbus A380 is the largest passenger airplane in the world. It's equipped with some of the world's most powerful jet engines and has a skin made out of a cutting-edge lightweight composite. Specially designed winglets make it fuel efficient enough to travel almost 10,000 miles non-stop. But how is it possible that a human can steer a plane this large and powerful? By the 1960s, the age of the jumbo jet was in full swing. Transcontinental travel had never been easier or faster. But a group of audacious engineers believed it was possible to take a jet supersonic.
There were a lot of engineers who said, well, this isn't possible. What you're proposing here is just too ambitious. The result of the work of those pioneering engineers is this, Concorde.
Launched in 1969, the Concorde could reach speeds of over 1,200 miles per hour. That's more than twice the speed of sound. Flight times between New York and London were cut in half. But flying a supersonic jet would be impossible using traditional aircraft controls. Concorde needed an innovative new system, a system now known as fly-by-wire. Former Chief Concorde pilot Mike Bannister explains, using a simulator at Brooklyn's Air Museum.
You could fly at 1,350 miles an hour, faster than a rifle bullet. Concorde wouldn't have been possible without fly-by-wire because some of the control forces at certain flight conditions really would have been huge.
What exactly is fly-by-wire?
Fly-by-wire is computers telling systems what I want to do. On a conventional airplane, when I want to turn left, I do that, and some pulleys and wheels and cables move the controls. On this airplane, when I want to turn, I do that. It tells a computer that tells the controls what to do. That means the airplane's far more responsive, it can be far more efficient, and is capable of being flown by ordinary human beings.
Concorde was the first commercial jet to use fly-by-wire technology.
What did it feel like to fly the real Concorde?
The airplane's delight to fly. It's like a thoroughbred racehorse rather than a riding school hack, or a sports car rather than a truck. It is so responsive. You can fly it with your fingertips. So why don't you have a go? Very nice. Keep it coming. That's perfect. Right through the bridge. London Assembly Building to the left, the Shard to the left. Fabulous.
Well, Concorde clearly is a remarkable aircraft. Not only is its exterior breathtakingly beautiful, but underneath the skin there is some technology that really revolutionized the aviation landscape and has made what we can do with modern aircraft today possible.
Since its first application on the Concorde, fly-by-wire systems have become industry standard. And on the Airbus A380, a highly sophisticated digital system makes flying the world's largest passenger plane possible.
For an aircraft the size of this aircraft is relatively a simple aircraft to operate. For flying, the aircraft is here, and it is completely electronic. I mean, there's no cables. It's all generating electrical inputs, which are sent to a computer, which then send the signal onto the flight control surfaces to move.
The design and development of the Airbus A380 ranks as one of the aviation industry's greatest achievements. Today, A380s are operated by airlines all over the world. One takes off and lands every 4 minutes. By drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own. Aerospace engineers overcame extraordinary challenges and succeeded in making the impossible possible.
It was quite difficult to imagine 20 years ago that kind of machine you have here was going to exist, but it's now reality. So what about the future? Who knows? Maybe going to the space with an aircraft.